Hello Year 12 and welcome to our first video here for networks. Brand new topic. In fact, a topic that you probably haven't ever studied before. Networks. Now it has to do with the way that things are related to each other. And we can think of it as a map of sorts. It's a map where direction and distance isn't very important, just what's connected to something else. Right, so it's very much about connections or links. Now it could be an electrical circuit, wiring in a house, or plumbing in a house for that matter. It could be a rail network, right? When you look at the map of train stations, where all the train stations are, that's a really good example of a network diagram. That the distances and even the directions on those things aren't in any way accurate, but what stations are next to what other stations and where you need to change, where the connections are, those are all the important parts on the rail network. Okay, so we use them in all sorts of things, and you can even think about your sort of social groups on Facebook or Instagram as a network. Okay. So this is what we'll be learning about. Here is a network. Right, you can see this here. It has some dots that have been labelled with letters. It's got lines joining them together. Now there's not lines between every single sort of dot there. And in this particular case, the lines, which we're going to call edges from now on, the edges have a number attached to them. So these are weighted edges, weight like mass, like how heavy something is. This is a weighted network. Not all networks that we'll be dealing with will have these weights on them, but this one does. So I use that language there. I called the lines edges, and I'm going to stick with that from now on. That's going to be the main thing that we're focusing on today, some of the new names for things. So the lines that connect them up are called edges. This particular diagram here is representing a road network. That's what it's to represent. 4 different towns, A, B, C, and D. And these numbers are representing the distance, the length of the road. So this tells me if I drive directly from A to C, it's going to be 10 kilometres. If I went via B, if I went from A to B to C, it would be 5 plus 3 would be 8 kilometres, so that would be shorter. I can't drive direct from B to D. I'd have to go through A to get there or through C to get there. And perhaps I could even go a long way around and go from B to C to A to D. Might not be sensible, but it's possible. It's not possible, according to this network here, to go directly from B to D. That's one of the things that it shows us. So, these little dots that are representing towns, we're going to stop calling them dots and we're going to call them vertices. So one vertex, multiple vertices. Okay, the dots are called vertices and the lines that join them together are called edges. These have numbers on them, so they're weighted edges, but they don't all. Some have arrows on them, and they're directed edges because they tell you what direction you can go, like a one-way street. Okay, so they don't all have arrows, they don't all have weights. Some of them have both, many of them have neither. But the dots are always called vertices, and the lines are always called edges. Now we have this thing called a path, right? A path is like going for like a walk along that network. So you can't magically disappear from one spot and reappear in another. It's got to be continuous. And a path is a special kind of route through that network that never goes through the same vertex twice. So it's like going for a drive and you don't drive through the same town twice. Okay, that's a path. Doesn't have to use all of the edges. You don't have to get back to where you started from. If you don't get back to where you started from, it's an open path. And if you do get back to where you started from, it's a closed path. And a closed path, well, you do get back to one town twice, where you start from and where you finish. But anywhere else you go, you pass through, you don't come back to it. That's a path. Righto. It's important to remember, networks aren't drawn to scale. It's just the connections between them, fancy word being the topology is important, but not directions and not distance. the degree of a vertex. I'm going to ask you questions about this in tests and things. I'll say, what is the degree of this vertex? To find the degree, you count the number of edges that come out of that vertex. Okay, so it says here in the diagram above, A and C have a degree of 3. Let's go back and have a look. Hopefully. Here we go. So you can see, here's the vertex A, and there are 3 lines coming out of there, 3 edges. There are 3 edges coming out of C as well. There are only 2 edges coming out of B, and 2 edges coming out of D. So the degree of vertex B is 2. 2 edges come out of there, that's the degree of a vertex. Right, we'll just skip through again. Now here's another word, and we're getting close to the end of the video really. To traverse a network, right, you can't always do this, but if you can, the way you do it to traverse a network is to find a route through that network that covers every edge exactly once. You can't miss any edges, and you can't use any edges twice. So there are really specific rules to help you calculate whether it's even possible to do this on a network. Certainly on some you can. Now, the main rule here is that only 2 vertices can have an odd degree. Right? So we find the degree of every vertex, and if there are more than 2 vertices that have an odd degree, so like 3 or 5 or 7 or 9 or something, then you can't traverse it, it's impossible. If there are only 2, then you can do it, and you have to start at one and finish at the other. I'll demonstrate that in a moment. And if all of the vertices have an even degree, you can traverse that as well. Rightio. Now I did promise we'd look at an example, and here we go. You're asked here to traverse this network. The first thing we're going to look at is the degree of every vertex. I have 5 vertices here, 1, 2, 3, 4, 5. The top vertex has a degree of 2. This vertex here has a degree of 4. See, 4 lines coming out of that. The one here at the bottom has 3, and this is symmetrical, so this one is 3 and this one is 4. So this vertex has exactly 2 vertices with an odd degree. The 2 at the bottom both have a degree of 3. These 2 here in the middle have a degree of 4, which is of course even, and the one at the top has a degree of 2, which is also even. So, according to the rules we learnt just a moment ago, this network is traversable, but only if I start at one of the odd degrees. So, there are a couple of ways to traverse this network. Here's one of them. So we started here at an odd degree, and I moved straight up. Then I went right up to the top, and back down again. I decided to cut across diagonally through the center of that network, back up again, back on the diagonal. Oh, I've done 2 there at once, down and across. And that is, you can see all of my edges were used exactly once. I didn't sort of take my pen off the page and come back somewhere else. It was one continuous route through that network. Okay, we didn't double up and we used all of them. That's what it means to traverse a network. So, to sum this up, what have we looked at in this video? A network is a type of map without a scale. It's made up of vertices, they're the dots, and edges, they're the lines. Paths never go through the same vertex twice. The degree of a vertex is the number of edges that come out of it. And finally, traversing a network means finding a continuous path from all the way around that network that uses every edge exactly once. Once, but not twice. Okay. Righto, that's it for our introduction to networks. If you've got any questions, please let me know. We'll be working in teams for the time being. Hopefully this made a bit of sense. Okay, I look forward to catching up with you soon. See you then.